Welcome back to my course Aspects of Biochemical Engineering. Now in the last lecture I tried to discuss the scale up of bioreactor, and I told you that this is a very important part of this course, because main purpose of the course of biochemical engineering that we want to apply that whatever things we develop in the lab in the bigger scale. So now question comes, whatever through the research work in the lab, day-to-day lab, we develop some kind of product. Now that we might have developed in a very tiny scale, maybe in the test tube, maybe in the conical flux, maybe in the 2 liter or 10 liter reactor, but that is not good enough for marketing the product. Am I right? So we shall have to go for the higher scale. When you go for the higher scale, that we should remember the monetary involvement of the process increased drastically. So, so naturally that when any investor, when he invested money, he should have 100% confidence that whatever things we get in the small scale, the same thing we should get in the bigger scale of operation. And that is why scaling up of the bioreactor is very much essential. Any kind of process, first we scale it up and try to find out that that whether under what circumstances we can develop the similar environment that we have small reactor and the big reactor. And so for doing so, there are certain operational parameters. As for example, power drawn by the agitator, I told you this plays very important role, and mild agitation, because we know in the microbial fermentation process that when you do the agitation, and as you increase the speed of the agitator, there will be some kind of shear effect, and due to shear effect the growth of the organism will be hampered. So naturally there should be an optimization of the power that to be applied in the agitator, and that is why we have a thing that is called biological concept of the process for scale up, and this tells that at what KLa or P by V ratio, power per unit volume of the reactor, that we will get the maximum amount of product formation. That because we say when we scale it up, we shall have to find out what is the minimum that power required for getting the maximum amount of product. Because industry, when you work with any kind of process, main concern is the money and the operation. That monetary involvement, because I told you that more power you applied, more current will be drawn, and that your money, the electrical power expenditure for the process increases drastically. So, and I try to give 2 different instances like penicillin fermentation and streptomycin fermentation, how the P by V ratio and the volumetric mass transfer coefficient, how that influence the product formation. Now this particular lecture I want to discuss 2 different problems of this scaling up of the bioprocess, and at the end I want to discuss the scale down of the bioprocess. Now first let me start with that with this problem. Now the problem says after a batch fermentation the system is dismalted. Dismalted means you just open it up, and approximately 75% of the cell mass is suspended in the liquid phase, that is the 2 liters, and while 25% attached to the reactor wall and internal with the thickness of calculated 0.3 centimeter. Cell mass productivity of the reactor is 2 gram per liter at 2 liter scale. What will be the productivity of 20,000 liter scale if both the reactor have height diameter ratio is 2:1? So this is the problem that so I can explain little bit what is the problem. Problem is that this is the reactor, am I right? And after the, suppose you put the media here and you put the cell here. So then after the fermentation you open the things, and initially this is 2 liter capacity, and if you say 75%, you take the liquid house and 75%, approximately 70% of the cell mass suspended in the liquid. So, what is the total amount of cell mass we have? This is 2 gram per liter mass, cell mass produced 2 gram per liter at 2 liter scale. That means how much is the cell mass? 2 gram per liter into 2 liter. Am I right? So, liter will cancel. So, this will be 4 gram. So, we will get the 4 gram of cell in 2 liter fermenter. Out of 4 gram, 75% goes in the solution. Am I right? I hope you understand that. That means this is multiplied by 3/4. That is 4 will cancel. So, 3 gram will go to the solution, that suspended liquid, and 1 gram remaining 4 minus 3 equal to 1. 1 gram 25% attached to the reactor wall and internal layer thickness of 0.3 centimeter. And height diameter ratio is given here, okay, 2:1. Now, you see that how we can solve this problem. The volume of the reactor, how we can write? This is this is pi r square h, am I right? This is the cylindrical fermenter. So, this is like this. Let us assume diameter is d. So, pi r square will be what? This is the cross sectional area. This is the liquid height, divided h. Now, r will be what? R will be d by 2 whole square into h. So, that is why we have write 1/4 pi d square into h. Now, h by d ratio is what? Is 2:1. So, if 2:1, I can write h equal to 2d. So, this is exactly what we have written, though this is like this. Now, this is equal to 2 liters, and one case this is 2 liter. 2 liter means 2000 centimeter cubed. So, we can easily find out what is the diameter, what is the surface area, what is the volume. That we can easily find out. Surface area is equal to, how you can calculate the surface area? What is the periphery? Periphery twice pi r. Am I right? So, 2r equal to diameter. Am I right? This is 2 equal to pi d, and height is h. So, surface area will be pi d into h. This is how we can calculate the surface area. Now, similarly, in case of 20,000 liter reactor, we can calculate the diameter. This is 233.5 centimeter. Surface area is this, and volume is this. Okay. Now, let us see how we can solve this problem. What is cell mass productivity? 2 gram per liter. And what is the volume of the small scale? 2 liter. So, I told you that how much cell will get for 4 grams. Out of 4 grams, 3 grams remain in cell suspension, and 1 gram attached with the cell wall, with the wall. It is the wall, is that fermented wall, that will be the 1 gram biomass is attached with the. Now, if you look at now, here we already calculated what is the surface area in 2 liter reactor. This is 734, am I right? 38. So, 1 gram of cell, that means 1 gram of cell is for 173 square meter surface area. So 1 gram cell present in 7 centimeter square, that we have already find out. And so, here in the bigger scale, how much cell will be there in the cell wall? This is 342,600. This is the amount of cell will be present in the as a cell wall, in the reactor wall, not cell wall, it is reactor wall. So this is exactly how we have calculated here. You can see how we calculate. We find out that how much gram of cell remain in the surface attached growth, that we find out. Now 2 liters we have this much. So now by in the 20,000 liters, how much will be there? Now by here we can find out like this, that this is 2 liter per liter. This is 75% is the in suspension. So I can in the concentration was 2 gram per liter. So 3/4 into 20,000, and the plus this is due to the attached growth. So total gram of cell mass you can get, that is about 30464.22 gram. So if no cell growth has been present in the 20,000 liter, then 400 gram cell mass. Thus cell wall if present can seriously alter the productivity the large scale upon the scale up. So that is one very interesting thing that we have, that material of construction of the fermenter plays very important role, particularly that usually the fermenter, the material construction should be stainless steel. Now as we know, the stainless steel may be of different types. That in the chemical industry we use SS314, and in the fermentation industry we use SS316. Sometimes we want some kind of special type of stainless steel. Now we add some kind of ingredient metal here, that is that so that the smoothness of the surface increases, so that the cell should not attach with the surface of the reactor too much. So this is a kind of analysis that has been performed just to find out that how much cell may attach with the surface of the reactor. Now next problem that we have, this is a simple scale up problem. Considered a scale up of fermenter from 10 liter to 10,000 liter vessel. Small fermenter has the height to diameter ratio 3:3. That means H is to D, this is equal to 3. So I can write H equal to 3D. Am I right? We can write the impeller diameter is 30% of the tank diameter. That means I, DI, impeller diameter is 30%. 30% means 0.3. That DI, DT, if we say that DT is the tank diameter, this is equal to DT, then we can write 0.3 into DT. The agitator speed is 500 RPM and 3 Ruston impeller are used, and this Ruston impeller looks like this. This is like this. Because you might be knowing that why we use the multiple starter. Let me explain again. Suppose you have one starter like this. Now in case of the liquid will go like this. So when it is rotated, so more you can see that most of the starting will occur at the bottom part of the liquid, not upper part of the liquid. But you want to have the homogeneity in the reaction mixture, so we shall have to have another impeller here, another, so that that here there will be started like this. So that is why they have written the 3 Ruston impellers are used. Determine the dimensions of the large scale and agitated speed by considering constant P/V ratio, and P/V means power per unit volume, constant impeller tip velocity and constant Reynolds number. Assume geometrical similarity referred to the given below. The geometrical similarity, let us assume that geometrical, let us remove that. Let us assume the geometrical similarity of the reactor. That means both are cylindrical reactor. So now let us see how we can solve this. So here what we have in this problem, initially we have 10 liter, and that is to be scale it up to 10,000 liters. Am I right? So this is the equation that we have. This is the volume of the cylindrical vessel equal to V equal to pi by 4 di squared into h, and we know that h equal to 3 di. Then we can write, this is the equation, and then we can find out that what is the value of di, because di equal to 0.3 dt, that is 30% of the tank, I already explained. And then we can find out what is the dt value, what is the h value, what is di value. So in the small reactor, the dimensions of the reactor we can easily find out. What is the height, what is the diameter, and what is the impeller diameter, tank diameter, all these things we can easily find it out. Now next is the 10,000 liter reactor. Am I right? 10,000 liter reactor. So you know that the scale up. So how you can find out that? I told you that V1 by V2 is equal to what? This is V is the 10 liters and V2 is the 10,000 liters. Am I right? So I can cancel it. So it is 1000. So this is 1 by 10 to the power 3. This is what? This is equal to di 1 cubed by di 2 cubed. Am I right? Now then I can write di1 by di2, this will be 1 by 10, because this is 3, this is also 3, this is a whole to the power 3 if we remove it, and then di2 is equal to di1 into 110, 10 times. So we can easily find out the diameter of the vessel. If you know the diameter, we can easily find out the height of the vessel, because we know for h by d ratio, that is equal to 3, and then also impeller diameter, we can 30% of the tank diameter is the impeller diameter, that we can easily find it out. So this is how we can calculate. Now let us come to the problem. Now the problem is that they are saying at constant P by V ratio, then what will the agitator speed? That means n value you have to calculate. Now P by V, I already mentioned that n1 cubed di1 square, n2 cubed di2 square. This is constant. Am I right? If this is constant, then we similarly previously we have already done that. We have seen n2 by n1 is equal to what? di1 by di2 to the power 2 by 3. Am I right? So we know this is 1. This is ratio is 1:10. So we can easily find out we know n2 value. So we can find n1 value we know. So n2 value we can easily find it out. Now if we assume, now question comes that if n1 value is not given, then we can write this into n1. Now if we assume n1 value is 1, then you can easily write this n2 value will be that time or as compared to the small reactor. Now next problem that we have, that is if when the tip for the constant tip velocity. Constant tip velocity means n di1 is equal to n di2. So if this is this, then what will be the n value? Then we can easily find it out, because this is n2 equal to n1 into di1 by di2. We put this value, we can easily find it. Now next is the Reynolds number. Reynolds number, what is this? N di square 1. This should be used in di square 2. Am I right? So this is first case, this is second case. If it is equal to this, then we can easily find it out. This N2 value is so it is very simple to calculate that what would be the value during the scaling up of the bioreactor. Different we can easily solve this. That how we can solve the different operational parameter during scaling up of the bioreactor. Now next thing that I am going to discuss, that scale down of bioreactor. Up till now we are discussing about the scale up of bioreactor. Now question comes, why the scale down of bioreactor is required? Because it's very simple. Because suppose I have been working with some 200 liter 200 cubic meter reactor, and we found that we want to study the effect of certain parameters on the productivity of the process. Now if we want to study that that effect of the parameter, that not necessarily always this should be positive, sometimes it may be negative also. So we cannot take risk for studying any parameter in the bigger scale. So what is required? We required that we shall have to scale down that. We shall have to that if you want to study some parameter in the bigger scale, first we shall have to study that in the smaller scale. I can tell you very simple instances. I work with citric acid industry, and citric acid industry, we know that we use some kind of industrial strain, and industrial strain, as you know, that is considered as a very stable strain, and the productivity of the particular organism remains unaltered after generation to generation. It doesn't depends on the generation of the organism, but still for the operation, for when we go for the full scale trial, full scale operation, production fermenter, we always run that same generation of the organism in the small scale, just to find out whether the productivity of the fermenter will be same or it will be going to change. If it is same, then and only then we from the same generation we prepare the culture and do that. Similarly, that suppose if we want to study any kind of parameters for this, we find out that whether this parameter is suitable, we can enhance the productivity of the process. What is the productivity? Productivity means amount of product that is produced per time. That is called. And what is the volumetric productivity? Volumetric productivity is the amount of product formation per unit time per volume of the reactor. That is called volumetric productivity. Now this productivity, if we find that if we want to study the effect of certain parameters on the productivity particular system, then first we shall have to do it in the small scale. That is we call scale down. We can study in the bigger scale. So this is considered the scale down of bioreactor. An efficient scale down bioreactor has to create the condition that will be representative for the conditions occurring in the large scale, and it is used for the optimization of the process condition and the operation. This is the main purpose of scale down, that we want to find out what is the optimum conditions that we have for this particular process. That that we cannot do in the big scale. We shall have to do always in the small scale, and that we always consider as a scale down. Now in the scale down, what happens is scale down is describe effect of fluctuating condition on the large scale bioreactor, because that because when you operate any kind of fermenter, it may so happen that operational condition may change. As I can give the simple example, that power failure. Power failure is a common issue of any kind of industry as per India is concerned. So though it is connected with DZ set, that power generation system, but it may require some kind of time, some kind of the time is required for start of the process again. So that kind of fluctuation, whether it affects the productivity of the system, that we can study in the small scale also and find out whether it is there or not. So it describes the effect of fluctuation conditions on the large scale bioreactor. The scale down approach focuses on simulating the laboratory scale and the environmental condition prevalent on the large scale and analyzing the effects of this fluctuation on cell physiology. That we can do it very easily in the small. This cannot be done in the big scale. Big scale it will be very difficult. Now scale down operation consists of following steps. One is the regime analysis. Regime analysis is very important. Regime analysis means, suppose I can tell you, suppose this is the agitation, am I right? This is agitation and this is aeration. The regime analysis is something like this. That means we shall have try to do this operation within this region. We cannot go beyond. As for example, if we go for this, if you go to this situation, what is this situation? Agitation is maximum, aeration is maximum. So here you can expect more shear forces. Now here you see, here agitation is less, aeration is also less. So here you have agitation and aeration both are less. That affects the fermentation process to a great extent. So you have to this regime analysis. So where you are going to operate your system, that you can easily do in the small scale. Then their simulation of laboratory system optimization and modeling of the culture that I have already mentioned, and application of the results on the large scale. This whatever we find out in the small scale, then we can apply in the whatever good results we have, then we can test it in the larger scale. So before we go for the large scale operation, it is always advisable to keep the run in the smaller scale. So in this particular presentation, I try to discuss some problem related with the scaling up. And when you scale up of any kind of bioprocess, I have given one example that when you produce the cell mass, but particularly I can give the example of Baker's fermentation process. Now there, that if cell produced on the cell that reactor wall, it is very difficult to separate it out. So that we shall have to find out that how much productivity of the process will be lost, and how much cell concentration will be in the attached, because with that we can change the material of construction so that we can have more smoothness on the surface of the material of construction, so that your less attached growth will be there. And second problem, we have discussed the conventional scale up problem, that how different other parameters can be monitored. And finally I discussed that what is the purpose of scale down. Scale down process usually we adopt when we operate any kind of bigger scale of fermenter. We want to study the effect of any parameters on the productivity of the process. That we cannot do in the big scale. We shall have to do in the small scale. And when you do that kind of study, we call it scale down. We shall have to scale down to optimization. Any kind of optimization study usually carried out in the smaller scale, not in the bigger scale. Thank you very much.